You guys asked, and I finally figured out the answer. What is Pogo with respect to a rocket, not a pogo stick, although there is some overlap? Today on Vintage Space. Alright, here's a rocket, and we are going to use this as our proxy model to explain what exactly is happening when a rocket experiences Pogo. But first of all, for those of you unfamiliar with the term Pogo as it relates to rocketry, it's the phenomenon when a rocket is vibrating along its longitudinal axis so hard that it's almost as though the rocket is bouncing on a pogo stick. That's where the phenomenon gets its name. So how exactly does a rocket like the Saturn V start vibrating so hard along its up and down axis that it's actually bouncing enough to impart G-forces on the spacecraft and potentially a crew on a manned mission? So there's a few things going on, but first off, I want you to keep in mind as we go through this explanation that as a rocket launches into orbit, there's a downward force being imparted on the rocket and on the crew. You hear them calling out that they're pulling G-forces. That's just by virtue of them rising up on a rocket. It's akin to the feeling you feel standing in an elevator when it suddenly starts to go up. You suddenly feel a little bit heavier because you're pulling slightly more than 1 G, or 1 times the force of gravity. So it can happen that as the rocket is rising, the downward force of its launch is actually pushing more fuel and more oxidizer into the combustion chamber that then ignites to power the engine to make the rocket rise. Now, if too much fuel or oxidizer gets into that combustion chamber, it can cause what's known as a surge. Now, this is something that engines do. It is a temporary increase in thrust. Now, this makes the rocket go upwards just a teeny bit faster and also increases the downward force on the rocket just a little bit more. But another effect of a surge is an increase in back pressure against the fuel coming into the combustion chamber. This back pressure reduces the engine's overall pressure, which in turn causes more fuel to flow into the combustion chamber, which can again cause another surge. Now, this can cause a feedback loop where the engine just keeps surging, and because the rocket is also rising, that surge can make the engine actually bounce up and down. If the engine starts surging and bouncing in a resonant frequency with the rocket's overall structure, the vibrations can actually cause the entire rocket to oscillate up and down. Now, the frequency of these vibrations can be felt in the cockpit by an astronaut as a bouncing motion going up and down. He would be pulling positive and then negative G-forces continuously as the rocket vibrates. Now, that's why Pogo is so dangerous. If the engine starts vibrating along the resonant frequency of the rocket, it can shake things loose. It can seriously harm astronauts. On Apollo 6, the Pogo on the first stage was so severe, it actually caused some panels of the lunar module adapter section to fall off. Now, granted, there was a manufacturing defect in there, but still, the Pogo was strong enough to dislodge a piece of the rocket's structure. Now, also keep in mind that as a rocket launches into orbit, it's burning fuel, so its mass is constantly changing. That and the fact that no two missions are ever exactly the same. The mass of the initial launch vehicle will also always be different. So there's a really good chance that an engine will vibrate in the resonant frequency of a rocket at some point during its launch. The Pogo problem first manifested when the US Air Force was testing Titan II missiles in the early 1960s, the same missile that NASA would then use to launch its Gemini program, and this caused problems for NASA. The Pogo was well outside the limits of what was acceptable to the space agency, knowing that a human occupant would be on top of that missile. Engineers ended up coming up with a solution to solve the Pogo problem, basically dampening out the vibration so that it couldn't get strong enough to be felt in the cockpit. The solution for the Titan II was to increase pressure in the fuel tank, add a standpipe in the oxidizer feed line, and add mechanical accumulators in the fuel lines. Solutions for the Saturn V were a little bit different because of its manufacturing. Fixing the Pogo problem when it reappeared in Saturn V launches was a little bit different because of the rocket's manufacturing. But NASA eventually took lessons learned and designed the Space Shuttle launch system such that it had a Pogo suppression system in place. The Space Shuttle main engines used partially filled gas accumulators attached by flanges to the oxidizer's turbo pump inlet duct. There were no serious Pogo instabilities throughout the shuttle program. So that, I hope, explains what Pogo is and why it's so dangerous. If you want to know a little bit more about how NASA discovered the Pogo effect and then ultimately solved it for the Titan II, the Saturn V, and the Space Shuttle main engine, check out my latest blog post over at Popular Science. There's a lot more information, and the link is below. Do you guys have more questions about Pogo or other strange rocket phenomenon that you don't totally understand? Let me know in the comments below, and of course, leave your other questions and comments and anything relating to old-timey spaceflight in the comment section as well. Be sure to follow me on Twitter and Instagram for daily vintage space content, and with new videos going up every week, subscribe right here so you never miss an episode.